Let's wait for 2 3 minutes. After that, I will start. Good evening. Good evening. So you people have got that assignment solution, right? Okay, let me start this recording. So this is week 3 problem solving session for the mathematical methods in physics. So what I have seen in the contents in the week 3, uh, mostly the operators are being discussed, and it is discussed about the eigenvalues and eigenvectors. So I'm not discussing again the assignment solutions because already you have got a very detailed solutions about the assignment question of week 1 or week 2. If possible, we can discuss it later sometime, maybe some other classes uh, where it will be easier for a detailed discussion. But right now, let us concentrate on the week 3 contents. Whatever is being discussed, I will give a review of that with some examples so that you can solve the week 3 assignment questions. So in between, I will put some questions, numerical questions, and that will be helpful. Okay, so the plan is today discussing about the operators, different operators. There are, of course, we have discussed some like identity operators. We have discussed adjoint. We have discussed. Today we will be talking about the projection operators, then Hermitian, then anti-Hermitian or skew Hermitian, and there are several others. So we will see each and everything, and we will see the eigenvalue, eigenvector problems, and finally we will see about the diagonalization. So all these things we will be doing today. Okay, so we will start one by one. Let me just switch off my camera. Okay, so we'll start today with the projection operators. Okay, so this is from where the weekly content starts. So I am also starting from that, the projection operators. So before that, before going to the projection operators or before moving to any operators, so the thing is that these operators are nothing but some kind of a matrix. Remember, these operators are nothing but some matrix. We use this term operators particularly in the quantum mechanics, where generally you have some wave function, say psi, or let's say I'm calling that as x. I'm not calling it psi. Okay. And a particular operator, whether it is projection operator or any arbitrary operator A, which is operating on this wave function psi, will give you this wave function will remain as it is, but with some physical value of this particular operator. These x are the eigenstates or the quantum states we generally define, and as this particular operator is operating on that wave function psi or x, it will yield a value, a magnitude. That magnitude is this lambda. And we will come to this particular equation today, and we will see that how to calculate this lambda, how to calculate these x vectors or the quantum states or something. But we will be dealing in here in mathematical terms. When you dive deep into the quantum mechanics, when you go in details the quantum mechanics, then you will find out that it will be easier to understand because ultimately those mathematics have been physically interpreted. Okay, so any operators is essentially coming from a matrix. Just remember that. Okay, so before going into these projection operators, let us understand first what is a projection vector. That is from where you will see that the projection operator, when you finally derive the expression of the projection operator, you will see that it is exactly the same. Okay, so this is the projection vector. So let's see what is the projection vector is. So suppose you have a vector A and you are projecting this vector. Let us say this is angle theta and this is another vector B. Okay, you are projecting this A vector on this B vector direction. Okay, so what you will do is that just drop a perpendicular. So this is your A cos theta. Up to this, the magnitude is A magnitude cos theta. Remember, this is the vector, it has a direction and as well as magnitude. I'm talking about here the magnitude. Okay, so this is the projection, and this distance is the projection in the direction of the B vector. Okay, so B vector has a unit vector, suppose B hat, which is nothing but the vector itself divided by the magnitude. This is what we all know, the unit vector definition. So in the direction of that unit vector, this is the magnitude we are getting. So the projection of A on B, that is understood now here. Okay, this projection is nothing but A into some cos theta into B hat. This B hat is because of the direction. This projection vector, remember this is a projection vector. It does not contain only the magnitude but also some direction. Direction will be what? Because you are projecting on the direction of the B vector, so it will be in the B hat direction. Now the magnitude is A cos theta. Fine. Now let us just keep this here And let us come to the derivation of the projection operators. So it starts with that you think about an orthonormal basis. So let E1, this E2, and so on up to En, these form and orthonormal basis. You can think it as this E1, E2, E3 as some x like I cap, j cap, k cap, and so on, higher dimensions. It does not matter. So right now, in the mathematical terms, we are writing n-dimensional vectors, unit vectors, E1, E2 up to En. Okay. So this forms the orthonormal. Why orthonormal? Normal means one unit magnitude. Okay. So these are all unit vectors. Just remember, orthonormal basis for some vector space. We have discussed this, that how to find out that a particular set of vector forms a basis or not. Okay, so this already we discussed in the last lectures. Okay, so space B. So this is the initial point, and we know in the from the last week's content that the identity operator, which is nothing but the identity matrix again. So operators are nothing but matrix. So I is generally written as like this. So I going from 1 to n, some I, small I, which is given by this. Okay, this is how the identity operator is given by. Okay, and let me tell you this thing. This particular expression is actually denoting the outer product. I will come to the definition of outer product very soon. Just keep this in mind. This is the outer product. This way of notation is the outer product. So I will come to it. So what is happening is that in this, I write this I as, see, I is equal to 1. I am just putting it here. Okay. E1. Yes. Sorry. What? Yes. Yes. But see, this is how the identity operator is defined, right? Yes. Okay. So what I am doing is that now from this I is equal to 1, I am just taking outside, and the other thing is kept here as it is. Okay. So this I can write. Fine. So now what I will do is that this E1 and this, I will keep it as it is, and I will take the all the other things on the left hand side. So I is equal to 2 to N. This is EI, and this is also okay. And I'm calling this as some kind of a projection operator E1, some projection operator, okay, which is defined like this. So oh, sorry. This is E1 and this is E1 again. So this is called the projection operator. You will see that how it is going to be similar to that of the projection vector. Okay, so this is the projection operator. Fine. Let me just show you. Suppose I operate this E1 on a vector x. Okay, some arbitrary vector x, like we have taken in case of this, some arbitrary vector a. Okay, so P1 on x means that you want to project any arbitrary vector x on the E1 direction, towards the E1 direction. Just like we have done any arbitrary vector, its projection towards the its projection towards the unit vector direction of B. Similarly, we are doing it here. Okay. So what will be the thing? If you are operating this, then what will be the resulting form? So it will be like this: E1 x, and finally this E1 can be kept here. Okay. So just look into this expression and look into this expression. These are exactly the same. Just look into this. See, this is what? This bracketed term is nothing but the inner product. And inner product and the scalar product are same in case of the real space. Right? So, x e1, that means what? It will consist of the modulus of x. It will consist of e1, which is the modulus of e1. It will consist of theta. That is, the theta is the angle between x and e1 vector. right? Times the E1. This is what? This is the unit vector, correct? In the direction of the E1. So this is the unit vector in the direction of the E1. One is its magnitude. So I am just multiplying one with it. X is the magnitude of that arbitrary vector which is being projected on E1, and this is the angle between them. Right? This inner product represents this, and this E1 always remains. So this becomes the unit vector. So you can see that this P1 of X, or the projection vector or the operator, is exactly same as the projection vector which we have derived. Only thing is that we have taken A and B as an example. Here we are taking as the orthonormal basis as an example. Okay, so these are the couple of things which we have seen. Okay, we have understood. Now, interesting thing is that, so I just write one line, which is important. So P1 projects this vector X onto the subspace corresponding to the project. So, okay, so P1 X will be in the subspace, that's fine. It's not an important thing. So P1 is projecting this vector X into the subspace like this, in this particular set of vectors, like in the direction of the E1. Okay, so this is the important. Okay, one important thing is that this x1 oblique x2. This is what we have already seen, that this is the inner product. In the real space, you can call it as a scalar product, dot product, whatever you wanted to say. So, in terms of matrix multiplication, it can be written as x1 transpose x2. And finally, it will give you one value, which is a scalar value. Okay, this you will get. But another thing is there, which we have just now written, is like this. See, this is only the notation. What it actually means is that x1, x2 transpose. This will not give you one value, but this will give you a whole lot of matrix. Okay, so this is called, the last one is called the outer product. So outer product and cross products are different. Just remember this. This is the outer product and this is the inner product. You can read about it later, but just I wanted to show that the notations are different and the definitions are also different. And the value it will yield is also different. Inner product gives you a scalar value, whereas outer product gives you a whole lot of matrix like some vectors, a set of vectors, I would say. Okay, let's see some properties of this projection vectors. The first property is that, so your this P1, you can keep it P1 or you can keep it P, whatever you wanted to keep, it's your choice. So if you just do P1 square, okay. So what you can write is that, so you have this E1, this, okay, and times another, right? This. All right. So what we can do is that the way to solve this is that, so this E1 remains. These two I will fuse together, and finally this. And you know that the inner product of E1 with Q1 is 1. Like I cap dot I cap is 1, J cap dot J cap is 1, like that. Okay. So this will remain, this will be 1, and this remains like that. So what I am getting is nothing but the P1. So what interesting fact which we are getting for the projection vector is that P1 square is equal to P1, which shows that it is an idempotent matrix. Idempotent, or idempotent, you can say operator or idempotent matrix. Whatever you wanted to say, you say. Okay. So this is one of the things. Second is, your, suppose you have P1 and you take a transpose conjugate. We are calling this as some dagger, P1 dagger. This dagger is the transpose conjugate. You take the transpose of P1 and then conjugate it if it is a complex plane, in the complex plane. Okay, so in this case, suppose you have the real plane and you can just see what you can do. Okay, AB dagger can be written as some E1 dagger and it can be written as E1 dagger. This is how you can write AB whole dagger, B dagger, A dagger. Okay, so this you can write. The interesting thing is that E1 dagger, this is in the bra notation, you can easily transform it into the ket notation like this immediately. Whereas this one can be transformed into the bra notation. Because of this dagger, I have removed the dagger, you come to this particular plane. So what is this? This is nothing but again the P1. So not only that it is an idempotent matrix which we have seen, but this is also a Hermitian. Okay. We will come to the Hermitian matrix, but you can call it as a self-adjoint matrix. Okay. So this is another thing. One important other thing is that uh, we can try to see that whether this, suppose P1 is there, is one projection vector as P2 is another projection vector. If you add this and take its whole dagger, will it be a Hermitian matrix or will it be Hermitian? So you can try out this, and I would say that, sorry, this I'm not saying this square. You take square. So what you will get is that ultimately, finally, when you try solving it, you will get P1, P2 and P2, P1 term. Otherwise, you will get P1 square plus P2 square. Simple algebraic. So this will become P1, this will become P2. But what about this? If this is equal to 0, then only you will get that P1 plus P2 whole square is actually equal to P1 plus P2. Okay, so this is, you have to see that how you can make this equal to 0. Only if these two terms becomes 0, then only you can prove that this P1 plus P2, if you add, that can be also termed as, can be used as a idempotent matrix or projection vector kind of a thing. Okay, so this is what I wanted to show about the projection vector and projection operator or matrix, whatever you say. Okay, so fine. Let me now go to the next thing, which is the eigenvalues and eigenvectors. The next thing. So what happens is that, so let's consider A is some kind of a linear operator. So let A be a linear operator defined in some vector space V. So your X belongs to V. Okay. So this X belongs to V, this vector space, some vector space V. Now, if you operate this A on this particular vector from the vector space V, X, you will get lambda times X. Okay. Now, generalizing, so for some complex number lambda. See, this is the general statement. Complex number lambda means it can have the real part as well as the imaginary part. So if you are in the real plane, so you will have this kind of a thing, lambda r plus iota lambda imaginary. Okay. But what happens is that when you are not dealing with the complex plane, you are only dealing in the real plane, this will be always the real value. So lambda r will be the lambda. Okay. So it depends. So generalizing this, we are saying that it is a complex number lambda. Okay, for some complex number lambda. Uh, so, and also x is called The eigenvector, of course, this is eigenvector of what? Of this A, this operator A, eigenvector of this operator A with eigenvalue lambda. So what we are talking here is that, so if you are writing it again, Ax is equal to lambda x. So this A is some kind of a linear operator, suppose, which is operating on this some vector, let's say x, that will give you that vector itself with some scalar quantity. This can be a complex number, generalizing, it can be a real also. It can be real, it can be purely imaginary, or it can be a complex number. Fine? And this x, which we were initially calling as a vector, these are the eigenvector corresponding to this particular value, which is called the eigenvalue, this lambda scalar value, the eigenvalues. And all these eigenvectors and eigenvalues are corresponding to this operator A or the matrix A. Okay, so this is what how it is defined, and there is a whole lot of spectrum that, so there can be many, like, so you have lambda one, you have lambda two, so it depends on the dimension of the matrix. So lambda one to lambda n is called the spectrum, the spectrum of A, or you can call this as the eigenspectrum of A. Okay, so this is the eigenspectrum. So if you have some n by n matrix A, which is operating on some n by 1 vector, which has n rows and one column, you will get n eigenvalues and x. Sometimes you may not get n eigenvalues. You can say that repeating eigenvalues are there. In that case, we will see what we call those. Okay, this is one of the things. Then I think it is introduced about some flipping operators. So, uh, so suppose this R is an operator. It is defined. This is just an example which is being given in the Week3 content I have seen. So this is an operator which flips actually this is an example. Let us okay that which flips the xy component. Okay, only the xy component. If you have a z, it does not matter. Only the xy component it will flip. So how it will be? Suppose you have say ex hat, ey hat, and ez hat. So what it will do is that if you operate this r on ez hat, which is a unit vector, it will give you ez hat only. There is nothing problem here. But r on ey hat, you will get ex hat. This is a flipping which is there, and r ex hat, it will be ui hat. So it's a flipping vector. Like if you are in the x direction, you will flip it into y direction. If you are in the y direction, it will flip it into x direction. Z has no change because this works on the xy component only. That's all. Okay, so this is an example. That's all. Now, another interesting thing is that this is another example. Look at the differential operator, ddx. Okay, ddx. And let us say that your eigenvectors e to the power kx. Okay, these are eigenvectors now. Just remember. Okay, since e to the power kx can be written as a matrix. Just you must know that it can be written. Okay, so what will happen if you just differentiate this? What will you get? You'll get k times e to the power kx. We all know this. This is the differentiation. First order differentiation, you can do this, right? So what you are getting, see, there is a vector e to the power kx. I have told you that this is some kind of an eigenvector. Let us consider. See, the same eigenvector is here, and there is a scalar value k, which is coming out here. And we can say that this is an operator, TDX. We know that integral, differentiation, these are all operators, right? We are operating on a particular function, and it will give you some scalar value times that particular function. E to the power x is a special one, where you will get this kind of an expression. Okay. So I can write from this particular expression that this e to the power kx are the eigenvectors. Okay, k is the eigenvalue, right? Eigenvalue in this is many eigenvalues can come. Okay, so what is happening now? This is okay. This is the first order differential. What about this d2 dx2 of e to the power kx? Simple differentiation will tell you what it will be what k square e to the power kx, right? Next d3 dx3 e to the power kx. What it will give you? K cube e to the power kx, and so on. If you go ahead and differentiate and finally come up to d dxn of e to the power kx, you will get k to the power n e to the power kx. Correct. So what you are getting is that if your a is suppose d by dx, okay, its eigenspectrum will be say suppose lambda 1, lambda 2, so on up to lambda n. Okay, depends on the eigenvectors. Okay, now if you have e to the power n, that means ddn of dxn, then what will be your eigenspectrum? It will be lambda 1 to the power n, lambda 2 to the power n, and so on up to lambda n to the power. Okay, so this is what is special about this particular example, where you have this kind of a differential operator and e to the power kx. So this is the example that how you can understand that the operator is being operated on a particular vector or a function. Okay, so this is one of the examples. Fine. Once we have done with these examples, then we come to different other operators. For example, let's come to the Hermitian operator. Hermitian operator. Important operator. We generally call this as self-adjoint. The most important property of this Hermitian matrix or a Hermitian operator is that your H is suppose the Hermitian matrix. Your H dagger, what is this dagger means? Just take its transpose conjugate. Just I am writing it here. Transpose conjugate. So you first what I mean, just transpose conjugate. Right? So you take the transpose of this particular matrix H and just wherever the iota terms are there, just make the sign change. Okay. So H dagger transpose conjugate of this Hermitian matrix becomes the Hermitian matrix itself. This is the important property, and this is the property which will tell you that whether a matrix is a Hermitian matrix or not. So this is a very important property which one must know. Okay, some other things about the Hermitian matrix is that, let me just show you that in this Hermitian matrix, if you write like this, a matrix, let us say a 3 by 3 matrix, and arbitrary elements are there. So it looks like this. See, this becomes D star, this becomes some, this becomes E star, this is B, this is F star, this is F, and this is C. Okay. So what is happening is that look at these elements D, E, F. These elements are the complex conjugate of those D, E, and F. Say D, E, and F. So you will see that the upper triangular part of the matrix and the lower triangular part of the matrix are exactly the complex conjugate of each other. Number one. Number two is that look at the diagonal elements A, B, and C. These A, B, and C must be always satisfied. Okay, must be from the real space. That means A, B, and C, the diagonal elements, the principal diagonal elements must be real. Okay, this is one of the important property. I think it's not much given in that particular content, but this is an important part that the principal diagonal elements of the Hermitian matrix or a Hermitian operator must consist of real elements, real value elements. That's an important part. Okay. Another important part, I think, as we go ahead, we will see that its eigenvalue are always real. It will never be imaginary or purely imaginary or complex. It will be always real. Okay, so I will come to it. It will be there. There's some properties which we can see. Okay, so another important thing is that, say, suppose you have A as some operator. If you are operating on some X, oh, you will get some Y value. Now, say x naught is some kind of a vector, okay, some arbitrary vector, let's say, and you do the inner product of x naught and y, you will get. We have seen that in the first content only. We have seen that this we can write. When you flip the things, the Tate and Bra kind of sign changes. You get a star complex conjugate. Right. This we have seen already. So there is nothing new about this. So what I can write is that this y x naught star, which is nothing but x naught y, can be written as x naught ax. Okay, this thing I am just putting it here, ax. Fine. So three together we just write it like this. Okay. What happens is that this x naught ax. Now, if you just want to flip this here and x naught here, what you will do is that you can write it as x a dagger x naught. See, x naught has come on the right hand side, and so it is just like this. So a x. Now, if you want to create it a kind of a instead of using the Tate vector, if you want to use the Brown notation, it will be like this. So you will have x and with a dagger or a complex conjugate kind of a thing. So this kind of thing happens. So finally, what we can say is that this y, if you want to write the Bragg notation of y, this is the case. Okay, so you have to write it like this: x and with a dagger. Things changes like this: a comes here and x becomes the instead of ket vector, it's a vector. It will be coming into the dual space. Okay, so this is what happens. You can see the proof in the content as well. So this we can run. And this is also an important way. We will use this for doing certain proofs, okay, to understand the properties of the Hermitian matrix. Why? Because you know that one of the important properties of Hermitian matrix is that you check the dagger, and this dagger here comes. Okay? So this is important. Okay, let's come to the properties one by one. Some properties I have already told you. Other properties let us mention one by one and see how we can prove it. So one is that these eigenvalues, as I was telling, that the eigenvalues of Hermitian operator or Hermitian matrix are always real. Okay, so let's say that H is the Hermitian matrix. And based on the very preliminary property, what we know about Hermitian matrix is that H dagger should be equal to H. This is known. Okay, assume that it is known. Let us consider that X be some vector. Okay, some arbitrary vector. So when you operate this H on certain vector, H of X, of course we will get some kind of a lambda with X. This is what we have seen in the eigenvalue eigenvector thing, right? Now, if you want to write it in the dual space, then what you will write? See X with H dagger. We have seen this. And in the dual space, what will this become? Lambda star and X. Because we are still not sure that this lambda is real or not. We are trying to prove that whether it is real or not. We are assuming that no, right now it is a complex number. This lambda is right now a complex number. We don't know whether it is a real or a complex number. Okay, so therefore we are taking this star sign or the complex conjugate sign because we don't know whether it is real or not. We are trying to prove that it is real. Okay, so this is what happens in the dual space. Fine. What we can write next step? X. H dagger is what? H. Nothing to change because H dagger is the H because it's a preliminary property of the Hermitian matrix, and we can write this. Okay. Now what we will do is that we will again operate this on the X itself. So X, H, and I'm operating on X itself. So here also, what I will be doing is that on the other side, we are writing this as lambda X, X, or we can write this as lambda star X, X. See, immediately from this step, if you are writing to this, you will get this, right? So let me just write in that way. Okay? See, this you are operating on X, what you will get? Lambda star X X inner product of these two because you are operating this same thing on X, both sides. So you are getting this. Fine. That's absolutely fine. But now look into this again. X, H, X, right? Now if you operate H on X, what you will get? Some lambda times X, and there is this vector which is always there. So what you will get? Lambda is a scalar which will come out. There is no problem in that. And you will get X, submit X. So same thing will give you lambda X inner product with X. The same thing will give you lambda star inner product of same vector X. Therefore, we can write that lambda star X inner product with X is equal to lambda X inner product with X. Correct? Now, the next step is that you bring this here, lambda star minus lambda X. This should be equal to 0. Right? This is what we are getting. Now, the thing is that, so the next important thing is that since now this X is not a null vector, we are assuming, we can write this term equal to 0. So lambda star minus lambda should be equal to 0, or lambda star should be equal to lambda. Okay, so this is what we are getting, that you will not get a kind of a real, sorry, the what you call as the complex number as this eigenvalue. This will always be going to be real. Okay, so this is what you have. Fine. So this is one of the things. Fine. What else is there? Okay. Next is, so this you will find out in the week content. Just I am just elaborating the steps. Next is the eigenvectors of a Hermitian matrix are always orthogonal. So we will see that Hermitian matrix. Okay. Important thing is that corresponding to distinct eigenvalues. This is an important point. Distinct eigenvalues. Distinct eigenvalues are orthogonal. Okay. So one of the properties of orthogonal is that your inner product should be equal to 0. We will see that. Okay. So fine. Let's see. Uh, Let us consider two eigenvectors x1, x2, and its corresponding eigenvalues are lambda 1, lambda 2. These are two distinct eigenvalues. Remember, lambda 1 is not equal to lambda 2. These are lambda 1 and lambda 2 are not equal. Distinct eigenvalues. Okay, this is what it is. So you have the Hermitian matrix operating on x1. What you will get? Lambda 1, x1. Same matrix operated on x2, what you will get? Lambda 2, x2. Simple. This is the eigenvalue eigenvector relationship. This we have seen. Okay. Next, what we will do is that let's take the dual space. So H dagger, which is nothing but x1 H, that will be lambda 1 x1. We have already x1 like this. We have already seen that this star, lambda 1 star is nothing but lambda 1, this which is real. Okay, so we can write like this. Next step, what we are doing is that we are writing x1 h, the same thing, and I'm operating it on some vector x2. Okay, so when you are operating on some vector x2, you are getting x1 operating on x2 like this. But again, the same thing, x1, h, x2, you can start operating h on x2 first and then put it with x1. So what it will that do? That will give you lambda 2, x1, x2. Okay, these two are things. So lambda 1, x1, x2 is equal to lambda 2, x1, x2. Okay, so lambda 1 minus lambda 2, x1 inner product with x2 is equal to 0. Since we know that lambda 1 minus lambda 2 is not equal to 0 because they are two distinct eigenvalues, so their difference is not equal to 0, then only we can say that x1 oblique x2 or the scalar product of x1 and x2 is equal to 0. What does that mean? x1 is orthogonal to x2. Okay. So these are the steps which are important. Like here also, these are the steps which are important. So in one case, we are directly writing. In the other case, we are operating this on this and then creating this operation to happen. Okay. Similarly here, we are first directly writing x1, x2. Second thing is that we are first operating this, then operating this on that. Okay, both are same. And finally gives you different results. From there, we compare and try to see that what we can uh, finally come out with. Okay, so this is another property. So remember that eigenvectors of this Hermitian matrix, if they have two distinct eigenvalues, will be orthogonal to each other. The states are independent or orthogonal to each other. Similarly, here we have seen that we have proved that we have taken once the complex conjugate, we have taken once the real one. The lambda first one is the real. Next, we have taken that. Let us say that okay, it is complex. We see that the complex and the real are same. That means it is. We have assumed starting. That the starting assumption was that we say that it is having the real, and finally we are getting that we are same. So it's a eigenvalue. Fine. So this gives you two important more properties. So one what we have seen is that your H dagger should be equal to H. Principal diagonal elements should be real. Eigenvalues should be real. And finally, we get that for distinct eigenvalues, distinct lambdas, we get your x1, x2 as 0 or orthogonal eigenvectors. Orthogonal eigenvectors. These are four important properties of uh, the Hermitian matrix. Fine. This is an important part. I will do another operator, which is called the unitary operator, and then we'll see that how we can relate these two. Okay. And I think some assignment questions are also there. You can easily do that from there. Fine. So next is the unitary operator. As the name, you can see that unitary, something unit magnitude thing will come here. Okay, so unitary operator. Okay, so we call a matrix or an operator as unitary when its adjoint is equal to its inverse. So what we are trying to say is that see here adjoint means the transpose conjugate, the dagger one. You can say that the transpose conjugate of U is equal to the U inverse. This is the definition of the unitary matrix. So again that part is that U dagger U is equal to U dagger is equal to I. The left inverse, right inverse kind of a thing. Okay. So this exists. Fine. Okay. So now what we will do is that, uh, okay, let's say y is equal to the unitary matrix operated on some vector x. Okay. Now, if you do the inner product with the same matrix y and y, this will give you a x. So, okay, just to remind you that if you do like this, what will happen? It will be x u dagger, right? We have seen that. So, x u dagger as this one, and this one is u x. U dagger is what? Identity. So, identity operator on x, which is nothing but x and x. That's all, right? So, what we are getting is that you start with y and y inner product, you are getting x and x inner product. So what essential information does it provide? It provides that it, its norm of this particular vector, if this unitary operation happens, if this unitary matrix operation happens on a particular vector, the norm remains the same. Okay. So initially you have a vector x, correct? You have a vector x whose norm is x oblique x, of course, with a root. Something is there, right? That is the norm's definition. Now, when you did the unitary transformation and did this to get some vector y, you will get the norm of that vector is same as the norm of the vector initially started. Okay, so norm remains the same, which is important. So for the unitary transformation or unitary operation will happen on a particular vector, it preserves its norm. That's an important property of this unitary operation or unitary matrix. Okay, let's go ahead with some other properties and try to see. Next is, this is one of the things. Next is your eigenvalues. Okay, this is the primary property. This is important. Just like we have seen the primary property of the Hermitian matrix, that is H dagger is equal to H. Okay, so here let's see about eigenvalues. Eigenvalues of unitary matrix or unitary operator, whatever you want to write, are unimodular, as we were talking about. Some magnitude equal to one, right? Unitary unit, one magnitude. Okay, so unimodular, it comes here. Some way it comes here. But what do you mean by unimodular? We will see. Okay, so first is you operate this u on some vector x and you get some lambda, suppose some lambda times x. This is the simple eigenvector eigenvalue relationship. Make it in the dual space x u dagger. This will be x, and you can write lambda star. Doesn't matter. Now what you do? Same. The inner product u dagger u x. What you will get? You get lambda star x and x. Correct. This is what you will get. Fine. What is the left hand side? U dagger u is what? Identity. So x I x. What is the right hand side? Just the same x. What is that? So what is this? This is nothing but x inner product with x. What is this? Lambda star x inner product with x. So what finally we can write is that lambda star minus 1. This should be equal to 0. That means what? This lambda star, that means the lambda times its complex conjugate will give you what? Mod lambda square minus 1. And this should be equal to 0 because you see x self inner product is not equal to 0. We know that. Okay. So this will be equal to 0 therefore. And mod lambda square is equal to 1. So this is coming entirely from the complex part, right? So you can see this. So this is mod lambda square, which is equal to 1. And hence we are calling the eigenvalues and unimodular. Okay, this is the part. Fine. So once this is done, we have another property, the third one, that now commenting about the eigenvectors. We have seen the preliminary properties, we have commented about the eigenvalues, where we see that the eigenvalues are unimodular. If it is a complex number, of course, otherwise it's one, the real one value. And let's see about the eigenvectors now. Just like we have seen in case of the Hermitian matrix. So eigenvectors of unitary operator or unitary matrix, whatever you want to say, again see, corresponding to distinct distinct eigenvalues are orthogonal. Again, almost similar, right? Just like the Hermitian matrix, almost similar. So let's see. You start with again u operated on x gives you lambda one x1. Okay, so let's start with x1 because you have to see that for distinct eigenvalues, right? So you have to take two different vectors. X2, you have lambda 2 x2. Done. This is done. In the dual space, x1 u dagger will be equal to some lambda 1 star and x1. Okay, so if you just do the same as we have done earlier, but the catch is that here we will operate this part on this. So u x2, because ultimately we have to prove that x1 and x2 are orthonormal or orthogonal. Correct. So that is what we are trying to see here. Okay. So on this side, what will happen? So lambda 1 star, which was already there, lambda 2 will come, and this will be x1, x2. All right. This is fine. U dagger u is I. So and also you have one important thing is that okay, u dagger u is equal to I, and we have also seen that lambda 1 star lambda 1 is equal to 1. So what we can do is that if we just write lambda 1 star lambda 1 of x1 x2 will be equal to lambda 1 star lambda 2 x1 x2. So what is happening here is that you're operating this u dagger u, this identity, on some way. Means if you just operate it on this will give you this lambda star lambda 1 star lambda 1, and on the other hand you will get this. So both way if you operate, you will get the left hand side as this, right hand side as this. So finally we will get lambda 1 star lambda 1 minus lambda 2 into x1 x2, that should be equal to 0. So since we have distinct eigenvalues, this cannot be equal to 0. So this has to be equal to 0. So x1 x2 should be equal to 0. This is an important part. Okay, and that proves that this is an orthogonal because inner product has to be 0. Okay, so this is what essentially we are getting. Fine. Okay, so these are orthogonal. Now let us see that how unitary matrix and your Hermitian matrix are related. I think one question is there in assignment. So let us do this. How they are related. So in one case, we have seen that A dagger is equal to A, which is the Hermitian. On the other case, we have seen that A dagger is equal to A inverse. Correct? These are the two things we have seen. So what essentially we are meaning? We are meaning that A is equal to A inverse. Means the matrix is its own inverse. That is an important part we are getting here. Okay. So what we start with here is that say A dagger A is equal to what thing? This is A dagger is nothing but A into A, which is nothing but A square. And A dagger A is also equal to A inverse A, which is nothing but I. Therefore, A square is equal to I. This is what we are getting. Now, this is only a matrix, right? We have to operate it on some vector. So, A square x, this should be equal to nothing but the identity. A square is nothing but the identity. So, you can write it like this Ix. What is the value of the identity operating on x? It's the self vector x, nothing else. So, what we are getting is that, or yeah, so if we are writing this as a square x, this will be nothing but lambda square x. We have seen this in the differential operator kind of a thing, and this is x. So what you are getting, lambda square uh, is sorry x minus x should be equal to 0. So lambda square minus 1 x equal to 0. This is non-null vector. Therefore, lambda square is equal to 1 or lambda is equal to plus minus. This is what we are getting. So the important relationship between unitary matrix and Hermitian matrix is that they can be related, or if a matrix is both Hermitian as well as unitary, then you will get the eigenvalues as some kind of this kind of a relationship as plus minus 1. Okay, so this is an important result. Finally, there is so much to go now. Uh, Let me just quickly go to another thing, which is the normal operator. Just quickly, I will uh, do this. Just wait a minute. Okay. Next is the normal operator. Simple. N is called the normal operator if n dagger commutes, like in dagger. This is one of the things. And generally, Hermitian matrix and unitary matrix are normal operators. So what does it mean? That operators commutes with its adjoint. Adjoint is this dagger which is written. Commutes with its this dagger. Okay, this is the. What else we can say about this? Okay, I just list it down. I'm not proving many things. There are several proofs which are there in the content. Go through that. But I don't think that much of questions will come from this part in the assignment. But you can always go through because if it is not coming here, it can come in the final exam. So just better to just look into it. Operator. If x is eigenvector, if I just list it down so that whenever if you have time to go through, you can just link it here with the content which is being provided and just go through it once again. Okay, eigenvector of n with eigenvalue lambda. Okay, so we can write something like this: n dagger x as lambda star x. Okay, this. is some eigenvalue. Nothing new here. Eigenvalue corresponding to any dagger. Okay, this is nothing new. It's all known to you. Next is eigenvectors of a normal operator corresponding to distinct eigenvalues are orthogonal. These things we have seen, right? Both for unitary matrices and all others, we have already seen this. So it's nothing much new about this. Okay, so fine. I think that's all. Okay. Next, an important property is the similarity and uniform transformation. So this is an interesting thing. Unitary transform, we have already looked into it that for the unitary matrix operation, the norms are preserved. So we have seen that. We will look into these things in detail right now. And then we will go to the matrix operation, how we are writing at matrix and solve the matrix equation. We calculate the eigenvalues and eigenvectors. And then we will go for the invertible matrix and then diagonalization. And that's all. We will finish up with some examples and certain properties that will help you to solve the questions. Okay, let us quickly complete this part. The next part is similarity and uniform transformation. I don't know whether it is uniform or not, but I think it is unitary. You just have to see. I may be wrongly written. Fine. Let's see. Let this A be linear operator on linear vector space V. S is some linear operator on the same space, on same LBS V. We define B as S A S inverse. So B is some kind of a transformed matrix which transform from this A to B. A is being now transformed to B using some S, is some kind of a linear operator as this kind of a transformation. Okay, so this is the transformation. This S in S inverse is a transformation. B is the transformed vector. Okay, just remember this or how to come to A again. So it will be S inverse BS. That's all. So just inverting that. Okay. One important thing is that now if you if this A is operated on X, it will give you lambda X. Correct? This we know. And let's say let Y is equal to S operated on X. S is also a linear operator which is operating on X. Now let us see some B matrix B which is operating on this Y. So what it will be? B S X, right? And what is your B? B, we have seen that this is A, S inverse, S X, right? This is B, fine. S, A, S inverse times X is identity matrix X. So identity can be removed. So S, A, X, correct? And A operated on X is nothing but lambda. So S lambda times X. What finally I'm getting is that lambda is of it. which is nothing but lambda y. So whatever is the lambda, look, the lambda which we started with when we have operated A on the vector x, the same lambda I am getting when I have defined a vector S operated on x as some vector and operated B on that vector. We are getting the same lambda. So A, B, A and B are similar operators, means that they share same eigenvalues. Okay, they share same eigenvalues. Of course, the vector must be defined in such a way, like S times X. This is an important part which I wanted to show. And I think I'm sure this is not uniform. This I think unitary transformation. Okay. So next is the unitary transformation. We have discussed about the unitary matrix. Similar to that transform is that suppose y you have u of x. See the norm of the vector remains unchanged. We have proved that norm of the vector remains unchanged. So whenever you do this kind of a unitary transformation, you will see that the norm of the x, the initial vector, will have the same norm as the final vector once we have done the unitary transformation. So this A unitary transform can be done like this. U dagger will A. This is how the unitary transformation looks like. And we know that U dagger is equal to U inverse. This is the same unitary matrix we are talking about. Okay, and this is also a kind of a similarity transformation, which we have seen just now here. Why we are calling this as a similarity transform? Because we are calling it as a similarity transform because look at this. Look at this transformation. U dagger if it is U inverse, we can write this as U inverse AU. Or from S inverse AS, the same thing which we have written here. We have written here S inverse or S inverse BS, anything. They are same, right? So essentially the same thing. So that's why we can call it as a similarity transform. Unitary transform is also a similarity transform. The most important part of the unitary transform is that the norm stays preserved. That's the important part. Okay, nothing else is much more important. Okay, next. So as I was talking from the very beginning, now it is mentioned in I think the week 3 content that operators are nothing but the matrices. Are matrices. That is important. All operators are nothing but matrices, which is an important thing. So again, we try to write the AX is equal to lambda x, the same equation where x are the eigenvectors, A is the operator on the matrix, which is operated on the eigenvectors x, and lambdas are the corresponding eigenvalues, which I have shown it in the very beginning. Now, to solve it, what we do is that we just take this and take x here, which is equal to 0. Okay. So in this, x equal to 0 is always a trivial solution. We have a trivial solution. It's a homogeneous kind of an equation where the right hand side part is 0. And this is a trivial solution which can always exist. But the condition, because we are trying to calculate the lambda, the condition for non-trivial solution is that your determinant A minus lambda I must be equal to 0. On doing so, so this modulus is nothing but the determinant, remember. So on doing so, what we have seen is that you put this equal to 0, but this is non-zero now. So I have some non-zero eigenvectors, and from this determinant, we will calculate the eigenvalues. That's how we do. Otherwise, x is equal to 0 can be a trivial solution. Just putting x is equal to 0, this is the solution. We can write. But we need a non-trivial solution to calculate the eigenvectors and eigenvalues. And for that, this is the best possible way. Okay. So let's see. Try further. An important point to note here is that the eigenvectors of a matrix corresponding to distinct eigenvalues are linearly independent. Okay, so let's see. So you have some lambda one and a corresponding eigenvector x1. Although we have still not seen with an example that how to calculate the eigenvalue and eigenvectors. We will see it very soon. Okay, but let us see. Lambda one is the first eigenvalue, corresponding eigenvector is x1. Lambda two is second eigenvalue, corresponding eigenvector is x2, and we can write this is in an equation like ax1 is equal to lambda 1 x1, ax2 is equal to lambda 2 x2. This we know, this is fine. Okay, and let us say that let x1, x2 are linearly dependent. What we have said, eigenvectors of a matrix corresponding to distinct eigenvalues are linearly independent. But we are assuming first that let us say that they are linearly dependent. We start with the false proof. Okay, linearly dependence. Okay, so how we can write this? We can write this as x1 is some alpha times x2. We can write this is the dependency. Okay, now ax1 therefore is alpha times a x2, which is alpha ax2 is what? Lambda 2 x2, which can be written as lambda 2 alpha x2, which is nothing but lambda 2 x1. So what I'm getting is very interesting. Ax1 is equal to lambda 2 x1. But what we have seen that Ax1 must be lambda 1 x1. And there are two distinct eigenvalues. And lambda 1 is not equal to lambda 2, distinct eigenvalues. Right? So since there are distinct eigenvalues, lambda 1 is not equal to lambda 2, and we have also seen that ax1 is equal to lambda 1 x1, ax1 is equal to lambda 2 x1 will never exist. It cannot happen. Therefore, this can't exist because of the these two reasons can't exist. Therefore, we say that it so this dependence, linear dependence is not possible. Okay, for distinct eigenvalues, if you say that the eigenvector vectors are linearly dependent, that is not possible. That's an important point which must be clear. Okay, this is another thing. Next is the concept of defective matrix. Defective matrix. Very important. We will see with an example. And while doing so, we'll know that how to calculate the eigenvalues and eigenvectors. There will be some question which will be coming. Okay. So defective matrix is that it's that matrix in which defective matrix is that matrix in which number of linearly dependent, linearly independent vectors of a square matrix is less than dimension of the matrix. So whatever example we will see today as a form of some question, we will take the lowest dimension matrix, like 2 by 2 matrix. Okay. Because these are easy to solve here, you can always solve the 3 by 3 matrix and perform the inverse operations and all. Okay. So here comes the question here that let us consider a matrix A which is 4, 1, minus 1. Okay, this is suppose a matrix. So first is that you calculate the eigenvalues and eigenvectors. Okay, this is the first part. Calculate the eigenvalues and the eigenvectors. So what to do? We know that Ax is equal to lambda x. We also know that A minus lambda I x should be equal to 0. And we want lambda and the vectors, right? So we cannot put x equal to 0. We will choose the non-trivial solution, that is the determinant of A minus lambda I should be equal to 0. For that, what we will do? Take the A matrix 4. Okay, let me go step by step, that will be easy for you. So this is 4, 1, minus 1, 2, minus lambda I then, so 1, 0, 0, 1, and put that equal to 0. So what you will get? So it will be 4 minus lambda. This will be 1, this will be minus 1, 2 minus lambda. Correct? This should be equal to 0. So remember, its determinant should be equal to 0. So just write a determinant here. Otherwise, everything will be problematic. Okay, so determinant should be equal to 0. So that means you have 4 minus lambda. You know how to calculate determinant, this cross. Okay, 4 minus lambda, 2 minus lambda, minus 1 into minus 1 is minus 1 and equal to 0. So it will be 8 minus 4 lambda minus 2 lambda plus lambda square plus 1, that is equal to 0. So lambda square minus 6 lambda plus 9 should be equal to 0, and just factor it. So lambda square minus 3 lambda minus 3 lambda plus 9 equal to 0, or you can say lambda minus 3 minus 3 lambda minus equal to 0. So lambda minus 3 whole square will be equal to 0. So lambda is 3 comma 3. Both the solutions are same. All right. So both the solutions are same. So lambda 1 is equal to 3. Lambda 2 is also equal to 3. Important thing is that these are not distinct eigenvalues. So we are finding, so we found that eigenvalues are not distinct. Values are not distinct. This is what we have found, right? These are not distinct. They are same. Lambda is equal to 3, 3. Okay, so let's check for the eigenvectors. So let's take lambda 1 is equal to 3 and see how to calculate the eigenvectors. So take this one, which one? This one. Okay, so 4 minus 3, this is 1, this is minus 1, and 2 minus 3. Okay, put some arbitrary x1, x2 as the element of the x vector is equal to 0. Correct? This is how the equation looks like. Okay. So now 4 minus 3 is 1. This is 1 minus 1, 1. And this is your x vector, x1 and x2, the elements as 0 and 0. You know that this is your eigenvector. Okay. This is eigenvector. X1, x2 are my choice. Anything can happen. Okay. So Let us multiply this row with this column, the simple matrix multiplication. So x1 plus x2 should be equal to 0. This is what we are getting. So x1 is equal to minus x2. So you choose x2 equals 1. So what will be x1? It will be minus 1. So both the cases, it will be something like this, right? This is the eigenvector corresponding to lambda 1 is equal to 3. This is the eigenvectors. Eigenvector, sorry. This is the eigenvector. Question is that for the lambda 2, there is a linear dependence of the eigenvector. If I choose x1 is equal to say minus 2 or x2 is equal to 2, then it will be minus 2. So which is a dependent kind of a vector. Correct. So in this case, we see when there is a indistinct, means the lambdas are same, then we call this matrix as the defective matrix. Why defective? Because look at what defective matrix says, in which the number of linearly independent vectors of a square matrix, it is a square matrix 2 by 2. 2 by 2 is a square matrix, right? Square matrix is less than the dimension of the matrix. What is the dimension of the matrix? N is equal to 2. The dimension is 2. Dimension is 2, but the number of linearly independent vector is only 1. This is the only one independent vector you can have. Next, lambda 2 is equal to 3. You can have this minus 2 too, which is dependent on this. Correct? Therefore, your this is a defective matrix. Why? Because your number of independent, independent, all are linear, independent eigenvector is 1, but dimension is 2. So 1 is less than 2. That's why it's a defective matrix. But if you only look at the lambda, that whenever you see that lambda is equal to same, lambda 1 is 3, lambda 2 is 3, and you cannot comment here, only looking at this, you cannot comment that whether a matrix is a defective matrix or not. For example, let us say you have the identity matrix. Let me show you. If you have the identity matrix, for example, okay, so it has dimension what? It's a square matrix having dimension n is equal to 2. Correct? N is equal to 2. And if you do the perform the eigenvalue operation, that is a minus lambda I is equal to 0, or here say suppose e is this, then what you will get? You will get the determinant as in the form 1 minus lambda 0 0 1 minus, and put that equal to 0. So what you will get? 1 minus lambda square is equal to 0, which will give you what? Lambda is equal to 1. So your lambda 1 should be equal to 1, lambda 2 is also equal to 1. You cannot comment here that it is a defective matrix. Why? You see, when you put this lambda 1 here, what will happen? 0, 0, 0, 0. Now it's your choice, right? Whatever you want to do, x1 and x2. Correct? You can choose x1, x2, anything. So you can choose 1, 0, you can choose 0, 1, and they are independent. There is no problem. Therefore, remember, defective matrix has to be chosen from the eigenvector, not from the eigenvalues only. Don't comment whenever you got lambda 1 and lambda 2 same. Don't comment that this matrix is a defective matrix until and unless you have checked up to this level. That choose the x1 and x2, see whether one eigenvector is dependent on another or not. Here it is not dependent on another, they are independent, but still the lambdas are coming to be same. So this is one of the examples of a non-defective matrix. So it's not a defective matrix, although eigenvalues are not distinct. Okay, this is important. Fine. How much time is left? Okay, 7:30. Something I have to skip, but important things I wanted to give. Let's come to the diagonalization directly, and yeah, we'll solve one question again, and then I will give you some important points to just solve certain questions there. and we list out certain things. Okay, just quickly go to the diagonalization. Other things you can see from the notes. Okay, diagonalization. So you have a matrix A. Okay, you can see it written like this: A11, A21, so on up to A n1. Let us say that it is a square matrix: 1, 2, so on up to A1n. This is A22, so on up to AN2. And this, if you go ahead, it comes up to be ANN, which is a n by n matrix. Okay. So the square matrix dimension is n. So n linearly independent dependent eigenvectors. Let us say that it has n linearly independent eigenvectors, which are x1, x2, so on up to xn. You can put the ket brackets that you can try. Okay, and corresponding to each eigenvector, there will be n eigenvalues, of course, which are lambda 1, lambda 2, so on up to lambda n. Okay, and each of these eigenvectors can be written like this: xi, say I can be 1, so x1, 2, x2, like that, can be written as like this: si1, si2, so on to sin. All right, so this is one of the things. Next, your a xi is equal to lambda I xi. This is also known. This is nothing new. So what we do is that we stack all the eigenvectors into a matrix. Okay, so let's form that matrix as S. You can also write it in terms of P. Any notation is fine. So S11, S21, and so on up to Sn1, S12, S22, so on up to Sn2, and so on, whatever you wanted to. So this is S. Okay, just remember one thing, that although I have written it like this is better to keep it as your x1, this is better to keep it as your x2, and this is better to keep it as your xn. Okay, so if you don't want to write like this, because this is confusing sometimes, so you can write like this. Okay, s let's say 1i, s2i, so on up to sni. Right. So that in case of x1, you have s11, s21 up to sn1. So this is your first eigenvector, second eigenvector, and like that. Okay. Because you will see that here I have a question that is easy to visualize. Fine. So already mentioned that your x1, x2, so on up to xn, these are linearly independent. This is already we mentioned. Only thing is that we have stacked now into a matrix. Okay. Now, what we will do is that this becomes now our uh, transformation to finally come to a diagonalized matrix. So you have S, this S, since it is linearly independent. So see how things are going. Since this X is linearly independent, what does that mean? Determinant of S must be not equal to 0. If it is linearly independent, look at the properties of determinant. So if you have a matrix where A, B, C is there, and you have 2A, 2B, and 2C, 3A, 3B, 3C. These are linearly dependent. What will be the determinant? Based on the properties of determinant, it should be 0. Correct? So if it is linearly dependent, if these vectors are linearly dependent, then determinant of S will definitely be 0. Since we are assuming that these are linearly independent, then only we can write that the determinant of S is not equal to 0. If determinant of S is not equal to 0, then S inverse exists. Okay? S inverse exists. Why? Because S inverse is nothing but 1 upon determinant S times adjoint of S. Correct? This adjoint of S, I have already explained how to calculate in the last lecture. You can go and see it. I think in the first lecture, just check it. It is there in the YouTube video. Fine. So these are the, so S inverse exists. In this, yes, its S inverse exists. Okay, fine. Now, what we do is that we have a vector, sorry, a matrix S. I multiply it with S, the vector which we have. So what we are getting is, I'm writing it once again. A11, A21, so on up to N1, and this is N1. Sorry, this is 1N, sorry, 1N, and up to AN. There are so many terms, we can just write it. Similarly, just multiply with this. So this becomes this 1N, and this. So it's an n by n multiplied by n by n matrix. Great. So finally, what will happen is that, see, these are all matrix operations which finally yields you this, right? Lambda 1 is 1 1, lambda 1 is 2 1, so on up to lambda 1 is in 1. Why? Because lambda 1 is common because this is nothing but the eigenvector x1. So when A is operating on x1, what do you get? Lambda 1 x1. Since these are all the elements of x1, this lambda 1 is common. So these lambda 1 will always be multiplied. Correct? Similarly, the second row, that's the second column becomes this. So it's 1, 2, lambda 2 is 2, 2, so on up to lambda 2 is n2. This goes, this goes, this goes. Lambda n is 1n, so on. Lambda n is n. That's all. This is what the matrix will come up. All right. Now, finally, so you have AS. Now, what you will do is that you do an S inverse of this. So, S inverse AS, what you will have is this lambda 1, lambda 2, so on up to lambda n. Only the diagonal elements will remain, and those diagonal elements are nothing but the eigenvalues. So why this diagonalization is important? Because if you have a matrix, if you have the eigenvectors of the matrix, when you do this kind of a procedure, that S inverse AS, do this kind of a diagonalization technique, you will find out the diagonal elements of that diagonalized vector as the eigenvalues. Okay, all other elements will be zero. All elements will be zero. Okay, only you will get this. So this is the diagonalized matrix. Diagonalized matrix with diagonal element as the eigenvalues. That is what is this diagonalization. This is the diagonalization gives you. So diagonalization of a particular matrix is given by this F inverse A is. Only thing is required is that you need the eigenvectors of that. If you have the eigenvectors of that, You try to do this to do this diagonalization technique, you will get the your this matrix with principal element with the uh, the eigenvalues. Okay, so this is what it is, and you can see that this is nothing but another similarity transformation. Right? We have already discussed similarity transformation. Okay, let me quickly write it down, which are not very important to elaborate. Just write it down certain things. Like number one is that an n by n matrix steps can be, these are some properties when you can diagonalize, can be diagonalized if it has n distinct, very important, n distinct eigenvalues. Okay, the roots of characteristic equation are all simple. Okay, what is the characteristic equation? This one is the characteristic. So A minus lambda I determinant is equal to 0. This gives the characteristic equation. Okay. So remember, only when it has n distinct eigenvalues. If you don't have n distinct eigenvalues, it cannot be diagonalized. So it is a conditions for diagonalization. Second is that the necessary and sufficient condition for n by n matrix A to be diagonalizable. Again, this is another condition to write all this, is that if or if mass have, which we have seen, n linearly independent eigenvectors. This is the necessary and sufficient condition. Third, another necessary and sufficient condition is that a matrix A, which is n by n, can be diagonalized. This is a property I think, diagonalized by a unitary matrix if your A is normal. Right. So important part is this: n distinct eigenvalues, n distinct or linearly independent eigenvectors. These are the two important conditions which needs to be satisfied. Okay. And finally, there is theorem which not proof. I will not prove here. This is Kelly Hamilton theorem. Essentially, what we are discussing. Okay. Essentially, what we are discussing is that for n by n matrix, A satisfies its own characteristic equation. So what does that mean? Suppose you have lambda 1, lambda 2, so on up to lambda n, then your E minus lambda 1 I, A minus lambda 2 I, so on up to A minus lambda n I should be equal. Okay, so this is the theorem, just I have noted. Now important part is a question which will deal with calculation of eigenvalues and eigenvectors. It's a 2 by 2 matrix again, easy to solve. And we will try to find out the diagonalized matrix. Okay, we will try to find out the diagonalized matrix. We will see whether we are getting the principal diagonal elements as the eigenvalues or not. Number one. Number two is that we will also list certain properties. Okay, so let us find out the eigenvalues and eigenvectors of this in the last whatever 12 13 minutes which is left. Okay, 1 4 2 3. Okay, so how to find out the eigen values and eigenvectors is that first you better you calculate the determinant of A. Okay, whenever A is given, you just calculate the determinant. So it is what? 3 minus A, which is minus 5. Excellent. That which is not equal to 0. Very good. If it is not equal to 0, that means it is linearly independent. Fine. But this linearly independent does not matter. Our P or that S matrix should be linearly independent. Okay, let's calculate the eigenvalues. For that, what you have to do? Cayley-Hamilton theorem. A minus lambda I should be equal to 0. You will get this 1 minus lambda, 4, 2, 3 minus lambda, and so this your determinant should be equal to 0. Do it. So what we will get? 1 minus lambda, 3 minus lambda, minus 8 should be equal to 0. So 3 minus lambda minus 3 lambda plus lambda square minus 8 should be equal to 0. Correct? Next is lambda square minus 4 lambda minus 5 should be equal to 0. Lambda square minus 5 minus 1 lambda minus 5 equal to 0. Lambda square minus 5 lambda plus lambda minus 5 equal to 0. Lambda minus 5 plus 1 lambda minus 5 equal to 0. So lambda minus 5 into lambda plus 1 equal to 0. So lambda is either 5 or lambda is equal to minus 1, or lambda 1 is equal to say 5 and lambda 2 is equal to say minus 1. Important thing is that lambda 1 is not equal to lambda 2. So they are distinct. Hence, they are not defective. Okay, this is important. Fine. Let's look at the important part and important property. Okay, you have seen the determinant, right? Determinant of A. Determinant of A is what? Minus 5, right? Now, if you just multiply lambda 1 into lambda 2, what will happen? So it's 5 into minus 1. See, this is minus 5. So remember, determinant of any matrix is the products of its eigenvalues, so on up to lambda n, if A is a n-value matrix. Okay, this is one of the properties important. Second is, there is a thing called trace of a matrix. What is this trace of a matrix? Is nothing but sum of diagonal elements. Diagonal elements. Sum of the diagonal elements. So what are the sum of the diagonal elements here? 3 plus 1, 4. So trace of A is 3 plus 1, 4. Just check one important thing. Lambda 1 plus lambda 2, if you do. So what will happen? This is minus 5. Oh, sorry. 5. 5 minus 1. That is 4. So another important property, the trace of A, and we'll generalize it for n by n matrix, will be lambda 1 plus lambda 2 plus so on up to lambda n. Sum of all the eigenvalues of a matrix is equal to the sum of the diagonal elements of the matrix, the trace of the matrix. Product of all the eigenvalues will give you the determinant of the matrix. These two are very important properties. Okay, will help you in solving questions. Fine. Okay. Now, I'll quickly, when I'm talking about trace, I'll just quickly mention you how to write this trace. So this trace of A is nothing but summation I is equal to 1 to n A I I. Correct? This is what it is. Diagonal elements A11, A22, A33, and you add it. What happens when you do trace of AB? So it is I is equal to 1 to n. This is how it is defined. Look at it. J is equal to 1 to n A I J B J I. Okay. I'll show you how it is being done. So say A is a matrix x1, x2, x3, x4. Alright, this is A matrix. Let's say another matrix y1, y2, y3, y4. This is suppose B matrix. You multiply this matrix, right? Because AB. When you multiply this matrix, x1, y1 plus x2, y3. x1, y1, x2, y3. Correct? Next, x1, y2 plus x1, y2 plus x2, y4. The second element. Third element, x3, y1 plus x4, y3. Fourth element, x3, y2 plus x4, y4. I am assuming you know the matrix multiplication. So this is the way. Fine. Now put it here. See, I is equal to 1. Okay. And j will go from 1 to 2 because here n is equal to 2 in both the cases. Okay. So you have a 1 1 b j is what 1 1 plus a I is still 1 j becomes 2 b j is 2 and this is 1. Correct? Look at the first this part. Isn't it A11 B11 plus A12 B21? It is the same, right? So this element is same as this, valid element. Okay. Second is when I is equal to 2. So A21 B21, sorry, B12 because J is 1 plus A. Now I is equal to 2. So 2 1, sorry, 2 2 because J is also 2, B2 2. This is what happens. See this element. Isn't it the same? A21, A21, B12, A22, B22. Right? So this is validity. Ultimately, this is the addition, which is giving you the trace. Correct? This is what is happening. This is how the trace AB is defined. Similarly, if you have to define trace of ABC, easy. Now you can define it like this. Three summations, I is equal to 1 to n, j is equal to 1 to n, k is equal to 1 to n because n is same, n is free everywhere. So A, it will be ij, B, it will be jk, and C, it will be ki. Okay, this is how you can define the case. Fine. So this is an important part which I wanted to cover. I think it is required. Just you see the assignment questions, it will be required. Now, finally, the last 5 6 minutes, let us complete the diagonalization. Okay, fine. So let's complete the diagonalization. We have already found out lambda 1 is equal to 5, lambda 2 is equal to minus 1. So, for lambda 1 is equal to 5, let us calculate the eigenvectors. So, it will be 1 minus 5, 4, 2, and 3 minus 5. And you have x1, x2, put that equal to 0. This is how you calculate the eigenvectors. This will be the eigenvector. Okay, so finally you are getting minus 1, 4, 2, minus 1. Oh, no, sorry. 1 minus 2, minus 4. This is 2. Sorry. This is x1, x2. Put that equal to 0. Any one you just choose and write. So minus 4x1 plus 4x2 will be equal to 0. So x1 will be equal to x2. Interesting. X1 is equal to x2. So let us say 1, 1. Let us choose the simplest. So x1 is 1, 1. Great. Corresponding to lambda 2 is equal to minus 1. What will happen? I'm just directly writing. It will be 2, 4, 2, 4. Just check. It will be like this. Put that equal to 0, 0. So you get 2x1 plus 4x2 equals 0. So what you get is x1 is equal to minus 2x2. So I choose x2 as 1 and this is minus 2. So this is your the second eigenvector x2 corresponding to lambda 2 is equal to minus 1. Now, what is the procedure? You stack it. So I am writing now p instead of s as this. So you have 1, 1, that minus 2. This is your transformation. And you know that you need P inverse. So just try that. So P inverse, okay, first let's see the determinant of P, that is equal to 1 plus 2, 3, which is not equal to 0. That means inverse increase. That's great. 1 by 3 and inverse in 2 by 2 matrix is easy. And this is 2 and this is minus 1. This becomes the P inverse. All right. So what is the procedure for diagonal analysis matrix? Is P inverse 8. So just try this 1 by 3, 1, 2, minus 1, 1. Original matrix 1, 4, 2, 3. And the P which we have got 1, 1, minus 2, 1. Once you solve it, you get 1 by 3 becomes 15, 0, 0, minus 3. And this gives you 5, 0, 0, minus 2. See, these are the lambda 1 and lambda 2. This is the diagonal. So you are getting the lambda 1 as 5, you are getting lambda 2 as minus 1. So this is how you try to find. So what will be the therefore the diagonalizable matrix P, which is we have found that is 1 minus 2. That's right. That is stacking the eigenvector. Okay, so this is how the diagonalization is made. Okay, and another thing I have noted, I think you know all these things, but still just Hermitian I have talked about. Just few notes for the assignment question solving, which is important. What I think it is important, that is about the skew Hermitian. Not much is mentioned. So skew Hermitian or anti-Hermitian are same thing. Here, a dagger is actually minus a instead of Hermitian where a dagger is a. Okay, diagonal elements. Here, diagonal elements are either real or purely imaginary. Okay, purely imaginary. What is the meaning of purely imaginary? Only iota term is there. Okay. Okay. Now, if A is Hermitian, suppose A is Hermitian, remember iota times A is skew Hermitian. Iota plus minus iota times A, whatever. Hermitian or anti-Hermitian, whatever you wanted to say. Anti-Hermitian. Same thing. Okay. This is one of the things I wanted to show. Second thing is about the symmetric and skew symmetric. Just quickly, I just write and we'll finish this. Symmetric is A transpose is equal to A. Hermitian was A dagger transpose conjugate, but here it is only A transpose is equal to A. And skew symmetric or anti-symmetric is A transpose is equal to minus A. The matrix looks like this. This element, the diagonal elements are 0. All other elements are just the minus of that, like this. Okay. So diagonal elements are 0. And we can write any matrix A as the sum of symmetric and skew symmetric. Okay. So yeah, that's all. This is what is the last. Okay. With this, I can end up here. If you have questions, you can ask right now or in the next class starting. Okay. I can. I think I have given too much of the information, but these are important. If you just go through, you will see that it will helpful for solving the questions. Okay. Yes. 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 Uh-huh. Correct. Correct. Yes. Absolutely. Any eigenvectors which you are saying like x1, x2, that can be energy level. Say, suppose E hat is the matrix, okay, which is operated on some x, some eigenvector, let's say, or some physical state, energy level, energy state, that will give you the magnitude of the energy of that level. Say x1 is that energy level, x2 is another energy level, x3 is another energy level, so on. This will give you lambda 1 times the same x1. That means this energy operator is operating on this energy level, gives you the magnitude of the energy as lambda 1 with the same eigenstate. Okay, this eigenstate can be energy, can be anything else also. Yeah. Correct, correct. So orthogonality is that they're independent. One state is independent of the other. That is what it says. Okay. Right. 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 Mm-hmm. Yeah. Okay. Okay. Welcome. Okay. See you next week then. I then stop that.